let's take a look at the MLE, the maximum likelihood estimate, for a PMF, probability mass function, on a finite set. So what do I mean by this? It's just what I'm saying here. So I've got some random variable x distributed according to some PMF p, and I'm going to assume that x just takes values in some finite set. So maybe it's, say, 1 to m, just some finite set. And p is a probability distribution on this set, so it's a PMF. So just a simple example would be if I had a die. You roll the die and maybe you get a 1, but it's any one of 6 numbers, and so then in that case m would be 6, and maybe p would be like a uniform distribution over these 6 numbers or something like that, or something close. So the MLE, so say we had some PMF determined by a die, then the MLE would give us a way to estimate, given a bunch of rolls of the die. It would be a method for estimating, say, the probability of getting a 1, for example. So for the MLE, the setup, what's the setup? So we want to figure out what the MLE is. So as usual, we have some data, little x through little x1 through little xn, and in this case, these are taking values in this set. And let's assume that we've got some random variables, x1 to xn, that are also going to take these values. So these are distributed according to p. And now for the MLE, we have to compute the some parameter. There's some parameter that is the MLE. And what's theta? So I'm going to use theta to be consistent with our previous notation, but what is theta here? I don't see theta. So theta is, well, what's this p? This PMF p is just, some numbers, p1, p2, etc. up to pm, and they sum to 1. So let's call these numbers, let's call p of I theta I. Right? So because each of these numbers is just, we could think of these numbers as being the parameters of this distribution. So let's call those theta I, and then we'll have our vector. We'll have a vector of parameters theta 1 through theta m, and that will be, we'll parameterize these distributions by this theta. So to make that explicit, let's maybe denote that this is, to emphasize that it's the p with that theta. Maybe we'll put p sub theta here. So this is parameterized according to theta. And let me also, to be consistent with our earlier notation, let's write it as p of I given theta. And by this I just mean, this is just the probability that x equals I given theta. So in this type of formulation, in this type of notation, we're thinking of theta as random. Here we're just thinking of it as some fixed, just some non-random number. But this emphasizes its randomness and makes it explicit what theta we're talking about. So the MLE, right, the definition is it's the argmax over thetas of the probability of our data given theta. Draw a line here. It's separate. So this is the MLE, and this was our data here. And so this is just, the probability that x1 equals little x1, right? So this thing here, what's this? This is just probably x1 equals little x1, and so on. Xn equals little xn, given under this distribution theta. Right. Okay, so now we want to find what the MLE is. So how are we going to do that? Now so the way that people usually do it for this type of distribution is using Lagrange multipliers. The first time I went through this, I noticed though that, or when I was going through this to make a video, I noticed that it looks to me like you need that method usually, the way that people usually prove it only shows that it's a critical point. and not that it's a maximum. And it's a bit tricky because you have a constrained problem here. So we're going to do it a little bit differently. We're going to try it. I haven't worked this out, but we're going to try to do it in a different way. And hopefully it will give us a correct proof, a full proof. Okay, so we want to compute this argmax. So we need some expression for P of D given theta. So first let's try to get an expression for P of X given theta. Just a single one, right? And then maybe we can get this from that. So what's this? Well, this is just, right, this is the probability that X, the random variable, takes this value. And that's just exactly what we defined to be theta sub I, or rather theta sub X in this case. Okay, so that's good. And now what's P of D given theta? So this is, right, this is the probability. This is P of x1, x2, up to xn given theta, which I just mean by this I just mean this, just a little shorthand. And because these random variables are independent, then this factors as the product as I goes from 1 to n, P of xi given theta, and then this is just, so this is just the product, theta goes from 1 to n, and we can plug in this expression here. So this is theta sub x, what is it? Theta sub xi. Okay. So now let's rewrite this so that there's a trick you can do which makes these type of calculations a little bit simpler. And I think we want to do it here. So we can take, let's say, the product from j, as j goes from 1 to m, of theta sub j to the indicator function that x equals j. So when x equals, right, so we're going for over each j, and when j equals x, then we get back theta sub x, and so it's, so because it's 1 then, and when x is not equal to j, or when j is not equal to x, then this is 0. So there's a 1 here, and those factors just drop out. So this holds, and so this thing we could have written, let's actually write it, theta sub xi instead as this product. J goes from 1 to m, theta sub j to the indicator that xi equals j. So why did I do that? Seems like just making things more complicated, but now we can switch these products, and I think we want to switch the products, and then see what happens. So if we switch those, we'll get the product over the i's on the inside, and then because theta sub j is just a constant, it doesn't depend on I, then we can the exponents just sum. So this becomes the sum of the indicators xi equals j over the i's 1 to n, and that, let's define that quantity, that sum. Let's give that a name. Let's call that n sub, so it only depends on j because we're summing over I, so let's call that n sub j. Okay, that's looking good. That looks like a nice expression, and these n sub j's here, we can give them, they have a natural interpretation because they are equal to, so n sub j, this is, so we're summing over the i's, and we're counting, so this is a 1 when xi equals j, and it's 0 otherwise. So this sum is the number of i's, it's the number of xi's that are equal to j. So this nj is a very natural thing. It's the number of i's such that xi is j. So that's nice. So we have a nice, very natural sort of expression here for this probability, this thing here. Okay, so that's looking pretty good. Let's circle that. Now we want to get the MLE. So we want to maximize this. We want to maximize this thing as a function of theta. So how are we going to do that? So let's oh, and it's not just I should be more explicit here. This is actually, it's not just the argmax over theta, it's the argmax over thetas that are PMFs, right? It has to satisfy this condition. So the sum of the theta i's, this is such that the sum of the theta i's is 1. So this is actually a constrained maximization problem, which makes it, more tricky. So how are we going to solve the constrained maximization problem? Well, I'm going to do something very sort of maybe non-intuitive here. And, well, okay, so the first step is intuitive. So maybe we can make it intuitive. So let's say, so we have a product, right? And a natural thing to do when you've got a product is take the log. Sums are usually easier to work with than products, so the log of the product is the sum of the logs. And that's just, well, let's move the n down, nj down, so we get log. So it's nj log theta j, summing over the j's. And so this expression here, if you're familiar with entropy, you might recognize this as looking sort of like an entropy. You've got a sum over some stuff. This is a probability, and there's a j here, so it looks kind of like entropy. So let's play with that a little bit and see if we can make it look more like entropy. Let's divide by n on each side. So this is going to become nj over n. Right? We can always do that. And if we maximize the original, the dividing by n, then that's just the same as maximizing the original thing. Oh, and I should have mentioned that, of course, maximizing the log of this is also the same as maximizing the original thing, because the log is monotone increasing. So if x is less than y, less or equal to y, then log of x less or equal to log of y. So maximizing the log is the same as maximizing the original function. Okay. So, alright, so it looks like I'm running out of time here. Let me stop this, and I will pick it up in another video. So I'll see you soon, and we will continue figuring out the MLE for this problem, a PMF on a finite set.